Hello friends, this video on DNF block elements part 20 is brought to you by examfear.com. No more fear from exam. Let's talk about the chemical reactivity of D block elements. See, these transition metals or the D block elements actually they vary widely in terms of chemical reactivity. Some of these are reactive, some of these are not reactive. Some of these are sufficiently electropositive that they dissolve in the mineral acids, while some of them are noble and they are not impacted by acids, simple acids. But actually, if you compare with S and P block elements, S and P blocks, transition metals are, or the D blocks, are the less reactive. They are less reactive as compared to S and P block elements. Okay, typically these transition metals they form bond with, you have seen, oxygen or halogens and sulfur. So due to the reaction between transition metals with oxygen, halogens and sulfur, you get oxides, halides and sulfides. And that's why we have seen that most of the transition metals are found in the ores, and these ores are typically halides, oxides and sulfide. If we talk about the oxides, transition metal directly combine with oxygen at high temperature to form oxides. For example, metal oxides, M2O3, MO, M3O4, MO2, M2O5, MO3, M2O. All these are different varieties of oxides. Okay, and all has this variable oxidation state. For example, this has +2 oxidation state, this has +1, this has this has +3 oxidation state, +5 oxidation state, +4. So now if you see, they have variable oxidation states. Now if we talk about the acidic and basic nature of this metal oxides, when these metal oxides are in the lower oxidation state, when they're in the lower oxidation state, they actually show basic characteristic. Okay, basic characteristic. For example, MnO, this is basic. Vanadium oxide, titanium oxide, these are all basic. Or FeO is also basic. When they are in the higher, when this metal oxides are in the higher oxidation state, we're in the higher oxidation state, they behave like acid. They have acidic character. For example, VO2, Mn2O3, CuO, right? Like this. MnO2. Example, if you see, MnO is basic, MnO2 is acidic. And when they are in intermediate oxidation state, in fact, Mn2O7 is actually has a higher oxidation state, +7. This is actually acidic. Okay, or let's take higher oxidation states, V2O5 or CrO3. Here we have +6 oxidation state, here you have +5 oxidation state. So these are all acidic. Or intermediate oxidation state, they are actually amphoteric. And the example for these are VO2, CuO, CrO2. These are all amphoteric. Even MnO2 is also an example of amphoteric reactor. Okay. Now the question is, why this lower oxidation state is basic and higher oxidation state is acidic? See, the lower oxidation state, some of the valence electrons are not involved in the bonding. Okay. The lower oxidation state, some of the valence electrons are not involved in the bonding, and since they are free, they behave as base. Okay. But in case of higher oxidation state, almost all the electrons, valence electrons, are involved in bonding. So no free electrons is available, and thus they accept electrons. So these guys accept electron and they act as acid. They have free electrons, they sometimes donate electron, and they act as base. Okay, good example, MnO is base, Mn2O7 is acidic, and MnO2 is amphoteric. Okay, the next is we'll discuss about the chemical reactivity of halides. So we'll talk about chemical reactivity of halides. Now we have discussed the oxides reactivity, acidic, basic, and amphoteric. Right? So halogen, again you take halogen, you take transition metal, again you do go for high temperature and you get halide. Similar to what we have seen, oxygen plus transition metal plus high temperature you get oxide. Similarly here you get transition metal halide. When you react halogen with transition metal at high temperature. If you talk about the rate of reaction, so in this case fluorine is most reactive, then chlorine, then bromine, and then iodine. Okay, and if you see, this fluorine actually forms ionic bond. Why? Because it is very electronegative. So if the electronegativity difference between two compounds is high, you get ionic bond. But these electronegativity is not that much, so it typically forms covalent bond with transition metal. Okay, and I have already told that the transition metal displays high oxidation state in case of oxygen and fluorine. And fluorine is again my halogen. So if you see, if you talk about CuFt for example, this is ionic. And if you talk about CuCl2 or CuBr2, these are covalent. Okay. If we talk about the sulfide, as I told, we'll talk about oxygen, halogen, and sulfur. Transition metal typically reacts with oxygen, halogen, and sulfur. So again, in this case, I have transition metal. It reacts with sulfur. You get sulfides. You can use sulfur, or you can also use actually H2S. Okay, for example, copper ions react with H2S to give copper sulfide and H plus ions. And in sulfides, we typically get low oxidation state. We have seen that oxidation state is higher only in case of oxygen and fluorine. Other cases, the oxidation state is lower. So in sulfides also, we have low oxidation state, and sulfides are typically colored. In fact, most of the transition metals or ions are colored. We'll see the property. And the sulfides are typically water insoluble. Transition metal sulfides are water insoluble. Now we'll talk about the chemical reactivity comparison with respect to standard electrode potential. Okay, please note this E0 is nothing but E0 reduction, and this is calculated against hydrogen, that is SHE, standard hydrogen electrode. Okay, this is for a typical reduction reaction. Okay, now if you see that one with the negative value of E0, see, if the value is negative, that means the reverse reaction is possible. For example, M plus 2 to M, if the value is negative, that means the reverse reaction, that is M to M2 plus, is feasible if negative. Okay, so if you see here, this value is highly negative. So this says that for titanium to titanium plus, actually E oxidation is nothing but minus of minus 1.63, that is plus of 1.63 volt. That means this reaction is highly feasible, and titanium has a tendency to get oxidized. That means titanium is a strong reducing agent. The strong reducing agent, because titanium has a tendency to oxidize itself, that means reduce other. Titanium is a strong reducing agent. Same thing apply for vanadium. If you see, vanadium to vanadium 2 plus, actually E oxidation comes out to be plus 1.18 volt. This is a big number. That means vanadium has a tendency to get oxidized, and vanadium is a good reducing agent. Same thing applies for chromium also. Same thing applies for manganese also. Okay. Now if we talk about oxidizing agent, let's see these values. Let's see the values of this one. Okay, Mn 3 plus to Mn 2 plus. This E reduction is positive value, it is plus 1.57. Since it is plus 1.57, that means this reaction is feasible. That means manganese has tendency to reduce itself. So manganese plus 3 is a good oxidizing agent. Please note, manganese plus 3 is a good oxidizing agent, not manganese plus 2. Right? Similarly, titanium and vanadium are good oxidizing agent. Sorry, titanium and vanadium are good reducing agent, not titanium plus 2 and vanadium plus 2. Okay. Okay, so magnesium plus 3 is a strong oxidizing agent. Okay, similarly, if you talk about this guy 1.97, is also a huge number. That is cobalt 3 plus is getting reduced to cobalt 2 plus. And in the meantime, this 1.97 volt of energy is released. That means it has huge tendency to reduce. That means it is a good oxidizing agent. So actually with the value of E0, that is standard hydrogen electrode value, we can actually tell or comment about the reactivity of transition metals. Okay.
Thank you. Visit examfear.com to watch more videos, attempt free online tests, get free study materials, find tutors and mentors, and much more. Thanks once again.